Okay, so today we have Gabriel Pedde Ungureanu, who will tell us about planar abelian mirror duals of n equals 2 SQCD3. Take it away.
Thank you, Julius, for the nice introduction and also for giving me the opportunity to talk. Yeah, as you mentioned, I will talk about the planar abelian mirror duals of n equal to SQCD in 3D. This is based on a work in collaboration with Sergio Benvenuti, Riccardo Comi, Sara Pasquetti, Simone Rota, and Anand Shri, and a paper which already came out, which is this one, and also on some work in progress, which hopefully should come out pretty soon. So first of all, let me tell you a bit about the motivations. So we want to study gauge theories as strong coupling, but as it's known, it's a pretty difficult topic to study. Also, supersymmetry helps a bit, but it's still pretty much an hard task to do. So we focus mainly on dualities, IR dualities, because they give us an important tool to shine light on some hidden features of a theory, which normally will not be visible, like some symmetry enhancement, as confinement, symmetry breaking, and so on. So if we have an initial UV description where some of these features are not manifest, we can go to a dual description where instead some of these become manifest, and this gives us more information about the IR theory, the IR fixed point these two theories flow to. In particular, through dualities like cyber duality in 4D, Aroni duality in 3D, and the mirror symmetry in 3D or 2D, we're sometimes able to study the strongly coupled region of a given theory, so close to the origin, by going to the semi-classical region in the dual theory, which is far away from the origin, where the theory is weakly perturbative. We can do computation with more ease, and so on. So what I will do in this talk is propose to you some new dualities for a family of n equal to SQCD theories with Chern-Simons level and chiral matter. The interesting features of the proposed dualities is that the mirror is always abelian, Lagrangian, and planar, as we'll see. So first of all, let me do a quick recap of mirror symmetry in 3D. So we'll focus on gauge theories in 3D from now on. So in 3D n equal 4 gauge theories, it was found out that this kind of gauge theories enjoy a particular duality called mirror symmetry. This mirror symmetry can be seen as acting in one of the following equivalent way. So the n equal 4 symmetry is given by SU2C times SU2H. So mirror symmetry can be seen as the exchanging of these two subgroup of the n equal 4 symmetry. Or equivalently, it can be seen as the exchanging of the Coulomb branch and the Higgs branch of the moduli space of these theories. Or also equivalently can be seen as the exchange of mass terms for global symmetries and Fayet-Iliopoulos D terms for gauge symmetries instead. Now, soon it was realized by Anani and Witten in 1996 that by embedding the gauge theories into string theory and by seeing these quiver gauge theories as the low energy limit of, in particular, type 2B string theory, mirror symmetry could be understood as the action of S-duality, which is a particular type of string duality which type 2B string theory enjoys, on the brane setup. And in this way, we are able to see this string theory interpretation of mirror symmetry. But now, what do we know about mirror symmetry with less supercharges, so in particular with 4 supercharges, so 3D n equal 2? So strictly speaking, mirror symmetry is not well defined since, of course, there is no clear distinction between an Higgs branch and Coulomb branch for n equal 2. But we can still call mirror-like duals those dual theories which come from n equal 4 mirror symmetry and are deformed to n equal 2. So we start with a n equal 4 non-mirror duality. We deform both theories in such a way to break a part of the supersymmetry, and we reach a new duality in n equal 2. And the dual theories we say to be mirror duals. So in the literature, there are proposed mirror duals for n equal to abelian theories. In this paper by Aroni et al. From 97, and also by Kapustin and Strasser from 99, where this abelian mirror symmetry was understood in terms of a Fourier transform. And also there are some proposals for non-abelian gauge theories by Sergio Benvenuti, Comi, and Pasquetti from 23, but The peculiar property is that the mirror theory involves these improved by fundamentals, which are these strongly coupled blocks which don't have UV Lagrangian description. So we would like to find some possible dualities where both theories are Lagrangians, because in this way they're easier to study. In particular, the family of theories that we propose in this paper is a family for n equal to SQCD theories whose mirror is about abelian, Lagrangian, and planar, as I mentioned. So let me tell you about the derivation. How did we come up with these new proposals? So we start from a known n equal 4 mirror pair, for example, n equal 4 SUN SQCD with F flavors, whose mirror dual we know, for example, from string theory. We know mirror dual is, and we consider a particular specialization of the Cartans of the n equal 4 R symmetry. So call the Cartan U1R times U1A. And now where this U1R in this specialization will become the surviving n equal to R symmetry after the deformation. Now what we want to do is to turn on a real mass for the commutant of this U1R. So in particular, give a real mass to those fields which are charged under this U1A in such a way that we are breaking explicitly this n equal 4 R symmetry to the n equal 2 R symmetry U1R, but in such a way that there is a surviving superpotential, which is the surviving n equal 2 preserving superpotential. And once we do this, we follow the trigger energy flow, both on the electric theory and on the mirror theory, and find what are the two resulting n equal to vacua on both sides, which are mapped one into the other. Exactly, we follow this deformation on the mirror theory, being careful in order to map the correct vacua. But okay, in practice, how do we do it? So in practice, we have a lot of tools to compute that give us information about the starting n equal 4 mirror pairs. What we focused on is the partition function, the n equal 2 partition functions of these n equal 4 theories, which were localized on S3, on a squashed free sphere. So these can be computed explicitly through supersymmetric localization, for example. So we know this partition function. So on the left, we have the n equal 4 partition function, which depends on these fugacities x and tau. X is the fugacity for the flavor symmetries, while tau is this fugacity that we turned on for the U1 axial Cartan inside the n equal 4 symmetry, which we want to break explicitly. Also, this partition function that we computed assigning some n equal 2R charges, which will be consistent with the U1R symmetry, which we want to break our n equal 4R symmetry too. So once we have this equality of partition functions, and once we assign these charges under the U1 axial, but the procedure of breaking their symmetry just turns out to mean turns out to be doing the following limit. So we take this equality and we do the limit where tau tends to infinity. So actually what this does is that we see that our partition function factorizes into two pieces. One piece which depends on this factor tau we sent to infinity, which is a pure phase, and another piece which is finite independent of this tau factor. It turns out that this phase phi is a highly oscillating phase, of course, for a very large tau, and is very sensitive on the Higgsing procedure that we do both on the electric side and on the mirror side. So then the reasoning is just perform this deformation, so this limit from the point of view of this free partition function, both on the electric side and on the mirror side. You obtain the factorization of the partition function into these two pieces, and if you are able to carefully match these two highly oscillating phases on the two sides of the equality, you obtain in the end a purely finite relation between these two partition functions, which we identify as the partition functions of the n equal 2 theories which we reached. So from this partition function, we are then able to read what is the n equal 2 theory which we reached through this deformation. So let me show you a clear example of what I mean. So we start from the SUN SQCD with F flavors, with F greater or equal than 2n, which is this, and its mirror dual, which is this one on the right, with the corresponding n equal 4 superpotential. So these two theories have been written in n equal to notation. So in this quiver, the double circled node represents an SUN gauge group. The square F node represents an SUF global flavor, global symmetry. The Q and Q tilde represent the two n equal 2 chiral superfields, which are in the n equal 4 hypermultiplet, while the phi is the n equal 2 chiral adjoint, which is in the n equal 4 vector multiplet. So we start from this theory, from its dual, and we perform the following deformation, the following real mass. Basically, we are giving...
In the chat, in India, he asks, what is the range of F that you consider?
What is the range of F that we consider? Just F greater or equal than 2. And basically, we consider only good theories. We didn't go to consider ugly or bad theories, so F is smaller than 2n, but we expect that this procedure should be could be applied also for this theory. Now, in those theory, there is this discussion that the mirror is actually given by a distribution of theories. So you have to be careful when you perform this limit because you need to check what happens to, you need to perform the limit of this distribution. So it's not trivial, and we did not see what happens. So we just focused on F greater or equal than 2n. So on the left,
sorry, I just wanted to ask that,
yes.
if F equals to 2n minus 1, then it's still a good theory.
It's an ugly theory at that point.
No, it's not an ugly theory. So it's actually a good theory. So there are no free hypermultiplets in it.
Okay, I see.
So for UN with 2n minus 1, yes, it's an ugly theory. But
okay,
SUN with 2n minus 1 is not an ugly theory. It's actually a good theory. And it has a known mirror, which has been worked out by different people. So
yeah, then, okay, we didn't try, but I expect it could be applied even in that case. Like the same reason could be applied. I said even in that case, even in the case of ugly or bad theories, can be applied without problems. But we did not try, so I don't really know what would happen, but we expect to obtain some result even in that case.
Okay.
Thank you for the question. So yeah, what we did here on the left side is that we gave a positive mass to the n equal 2 chiral in the anti-fundamental Q tilde, and because of the n equal 4 superpotential, this forces us to give a negative mass to the n equal 2 chiral adjoint if we want to preserve the n equal 2 fundamentals Q. So we flow to this electric theory where it's just SUN with F fundamentals at Chern-Simons level for the non-abelian SUN at level F alpha minus n with 0 superpotential. Now, what we claim is that the correct mirror, if we follow carefully the deformation at the level of the sphere partition function, is the following. So you see that what happened is that each one of the UN gauge node got adjoint x'd to the maximal torus, so U1 to the n. And then you have the leftover n equal 2 chiral multiplets, which form these triangular loops between the adjacent gauge nodes. And you also have some surviving superpotential terms, which is this W planar, which comes from the n equal 4 superpotential surviving terms. And then you also have some extra contribution, which we'll see explicitly, which is this monopole contribution, which comes from the adjoint Higgsing of the gauge groups, which is actually necessary in order to have the correct matching of global symmetries, as I will show, because each one of these gauge nodes in the n equal 4 theories carries a U1 topological symmetry. So when you are Higgsing it to U1 to the n, you would expect to have n topological symmetries in the end. But actually, because of this monopole superpotential, which gets generated, you just have one topological U1 symmetry for each column. So for each column, you basically have n-1 superpotential terms which are generated, which break the topological symmetry down to a single U1. And then, sorry, in this is just a depiction. There are also Chern-Simons levels. So for each black U1 node, you have a generated Chern-Simons level at level -1, while for the red node, you have a Chern-Simons level at level -1 alpha. And also you have a mixed Chern-Simons interaction between adjacent gauge nodes connected by links, which is at level +1 for horizontal and diagonal links, and a level -1 from vertical links. These BF terms, which are mixed Chern-Simons interaction, also come from the n=2 chiral method, which has been integrated out after the deformation. So exactly as I said, this is the correct vacuum which gets mapped to. So basically what this deformation does on the mirror side is that it forces the lowest component scalars of the n=2 vector multiplets on the right to acquire waves in such a way that this is the pattern the theory gets Higgs to. And this also generates monopole superpotential, as was studied in this paper by Polyakov in 1977. So yeah, what we claim is that the corrective vacuum is the one where the lowest component of the n=2 vector multiplet for each case node, which we call sigma, takes waves in such a way that the difference of the waves between adjacent vertical nodes is equal to m, where m is the positive mass that we turned on the electric side. So it's the positive mass that we gave to the Q tilde to integrate them out on the electric side. And we also checked that this Higgsing satisfies the one loop equation. So it's actually a consistent solution of the equation of motion. So a consistent vacuum. And the remaining massless matter, which is not integrated out, transforms us by fundamentals in these loops shown in the diagram. Now, what are the checks that we were able to perform in such a way to support our proposal? So first of all, the rank of the global symmetries match. So on the left, we have an SUF flavor global symmetry times U1 baryonic global symmetry. On the right, we have F topological symmetry. So the rank is the same. And what we claim is that these F topological symmetries enhance in the IR to an SUF topological symmetry, which is mapped to the SUF flavor symmetry on the electric side, times a U1 topological, which is instead mapped to the U1 baryonic on the left side. Moreover, the matching of the S3 partition function, besides providing a neat derivation, also provides the strongest test of our proposals, because it's an equality between partition functions, so it's by itself a strong check. And also we were able to perform, at least for some fixed values of n and f, so for small values, for example, n=2, n=3, and f=4, 5, 6, 7, and so on, we were able to check that the first few orders of the superconformal index, so of the partition function localized on S2 cross S1, matches on both sides. Now let me provide an explicit example to make it more clear. So this is the deformation which comes from SU2 with the n=4 theory, which is SU2 with 5 flavors. We perform the real mass deformation on the left and on the right, and this is what we obtain. On the left, we obtain SU2 at level 1/2 with 5 fundamental chirals, no superpotential. On the right, we obtain this theory, which is, as I mentioned, completely abelian, is Lagrangian, and it's planar, so to say, because the n=4 linear quiver opened up, forming this planar quiver of U1s. And you also have this cubic superpotential, which I wrote explicitly, between the edges of the triangles in the theory. And you also have this monopole superpotential. This notation means that these are actually the topological charges of the monopole under the U1 topological on the mirror. So each U1 in the mirror carries a U1 topological charge, and these are the charges of these monopoles under these topological charges. So we see that these are charged in such a way that they break the two U1 topological of each column to a single U1 topological. This is necessary to have the correct matching of global symmetries. So yeah, so if we give this assignment, as I said, the Q are in the fundamental of SU2, so in the anti-fundamental of SU5, they have baryonic charge 1/2 and trial are charge 1/2. On the mirror, you have the diagonal and the horizontal, which have trial are charge 1/2, and the vertical, which has R charge 1, so the cubic superpotential have R charge 2. Now, to give checks for these theories, a quick way to, nice way to map the operator map is to encode the information about the charges of the monopoles, I mean both gauge charges and the charges under topological symmetries in this polynomial. So this polynomial, which tell us the charge of a generic monopole whose topological charges are as the one appearing in the superpotential, or even with different topological charges, the contribution to this polynomial come from one-loop corrections, so fermionic zero modes in the this is a sum over all fermionic zero modes in the theory, and then you have two contributions. One which comes from Fagletti-Iliopoulos terms, which observe that for each U1 gauge node, we have these blue terms, which are actually the Fagletti-Iliopoulos D terms that we have to turn on for each U1 gauge node. These are necessary for the duality to hold. And the last term is instead a sum over the Chern-Simons interaction and the mixed Chern-Simons interactions in the theory. The UI and UJ are the gauge fugacities. So using this schematic formula, we are, for example, able to check that these two monopole terms appearing in the superpotential are, first of all, are gauge invariant. They are not charged under topological symmetries, and also they have R charge too. This constant part in the charge is just the R charge. So they have the correct values of charges and R charges to be turned on in the superpotential. So this is already a nice consistency check. And also if we want to do the operator map, on the left we have 10 baryons. We claim that 10 baryons, these 10 baryons are mapped to these strings of monopoles, which basically these are just monopoles which are all charged under the topological charge under the red node, and then you have these Young tableaus of minus charges along all the rest of the theory. So you can check that this is consistent. So the baryons have R charge 1 with our choice of trial R charge, and they are in the true index antisymmetric of the SU5 flavor symmetry. So by using our monopole formula, we are able to check that the monopoles that I just presented have the correct charges, so R charge 1, and seem to transform actually in the true index antisymmetric of the SU5 flavor symmetry. So this is consistent with the proposed map, which is also a nice check. And also another check, as I said, is the match of superconformal indices. This is the N = superconformal index. The bold numbers are a representation of SU5, or the SU5 flavor symmetry, while the F is the U1 baryonic. So we can see that effectively also on the mirror side, the monopoles rearrange themselves as a representation of SU5 in the IR. And also at order x squared, you have the correct characters that you would expect. The 24 is the adjoint character of SU5 plus 1. So you have, as a global symmetry, as a conserved current, the SU5 cross U1 conserved current contributing to the index. We also computed, we can also compute the Hilbert series for these two theories, which is just given by this formula. At order T, we have the 10 baryons. So this is the representation they transform into in terms of Dynkin labels. So the 0, 1, 0, 0 is just the true index representation. And then at higher orders, you just have products of these baryons which satisfy quantum relations. While also on the mirror side, these are mapped to the monopoles. We again have the 10 monopoles in the true index antisymmetric representation of SU5, and they also satisfy non-trivial quantum relations at higher orders. Now, this strategy can also be applied to more general theories, for example, to linear gauge theories as well, to Quiver gauge theories as well. This is an example for the TSUN with n equal 3. So in the n equal 4 case, the mirror symmetry is a self-duality between the two theories. Now, when we do the real mass deformation, we go to n equal 2, this becomes a duality between a theory which is completely chiral and non-abelian on the left side, and a theory on the right which is planarized, it's completely abelian, you only have U1 gauge nodes and flavor nodes, and is Lagrangian. The operator map is that, so on the right you have these two mesons which just come from starting from one square ending to the other, and these are mapped to two dressed mesons on the electric side, which are not trivial to see. But also, okay, you could ask, I gave you some examples. How do we make this more general? How do we make this more systematical? So what has been done for n equal 4 is that an algorithmic approach to mirror symmetry has been developed on the assumption that mirror symmetry can be seen as the action of some local operators on the field theory. So from the point of view of string theory, if you consider your brane setup, whose low energy limit is the Quiver gauge theory, giving you your 3D n equal 4 theory, what you can do is that you can insert between each NS5 and D5 this identity operator in the form of S times S minus 1, where the S is the local operator, sorry, is the operator which implements the local action of S duality in type 2B string theory. And then you say that each S to the minus 1 and S is sent to a D5, while each S to the minus 1, D5S is sent to an S and an S. And what you obtain in the end is your brane setup corresponding to the mirror theory, whose low energy limit will correspond to your 3D n equal 4 mirror theory. Now, these has actually been studied from the point of view of field theory. So again, in field theory, we can try to implement this local action of S duality. So the equivalent of the S operator in field theory is given by the TSUN theory, which I presented before, which is just this quiver with increasing ground gauge nodes with a manifest SUN global symmetry at the end, which enhances in the IR actually to give you two global SUN times SUN global symmetry. The other SUN is just the collection of n-1 topological symmetries which enhance to an SUN. And now the claim is that the basic duality of string theory, which is S to the minus 1 D5S equal to an S5, is implemented in this way in field theory, but by what is called a braid move. So you have this flavor, this bifundamental flavor, which is sandwiched between two FT, and the claim is that this corresponds, similar to string theory, to the basic building block corresponding to the NS5, which is this bifundamental. And so, okay, this may seem very abstract, but it can be proved at the level of only in QFT by only the action of local Aroni duality. So for n equal 1, what you obtain is just the basic n equal 4 mirror duality, which tells you that a U1 gauge theory with one flavor is S-confining. So it's dual to West Domino bifundamental. But the same can also be proved for n greater than 1. So this is the example, the sequence of proofs for n equal 2, which tells that this theory, written in a Lagrangian form through a specific sequence of application of local Aroni, can be proved to be S-confining to this simple bifundamental. This A is just the action of the local Aroni duality, and the circular orange node is the node that on which we act by local Aroni at each step. Okay, a review of Aroni duality is just that it's a duality of 3D n equal to gauge theories, which tell you that U1 with F fundamentals and anti-fundamentals and no superpotential is IR dual to UF minus n gauge theory, again with F fundamentals and antifundamentals, and also with a superpotential, where you also have the mesons, which are in a cubic relation with the fundamentals and antifundamentals, and you have these linear singlets, gauge singlets S plus and S minus, which are linearly coupling to the local operator charged under the U1 inside of the UF minus N. So there are also further ingredients that you need to implement the local action of S duality at the level of the field theory, which is the fusion to identity, which is just the statement that S times S to the minus 1 is equal to the identity, which from the point of view of field theory is that when you glue two FT theories, this gives you the identity operator, which is a product of delta. This, from the field theory point of view, is just the statement that the theory presents a quantum deform moduli space, which means that everywhere on the moduli space, the global symmetry is actually broken from SUN times SUN down to a single SUN. While you can also get the inverse basic move from the basic move, which it just tells you that the simple bifundamental block is dual to bifundamental and SUN times SUN, glued, sandwiched between two T of SUN. Again, all of these can just be proved through the local action of Aroni duality, which I will not prove, but okay. And then the claim is that with these basic moves, and also with, okay, from the point of view of the brain setup, you also have the Anani-Witten duality move, which is given by the exchanging of NS5 and D5s, which is necessary to have the canonical interpretation for the low energy limit of the brain setup, giving you the quiver gauge theory. What you are able to do is that you are able to locally dualize any N=4 quiver. So you can consider just a longer quiver, where these are just some pieces in the quiver. Then what you do is, again, as from the string theory point of view, you insert the local operator S, which is given by this T of SUN theory. You insert S to the minus 1, which is just the insertion of the identity operator, as I showed you. And then you identify the basic move, which I showed you before. So this is the basic move. Then the second one is the inverse of the basic move. And then again, you have two other basic moves. And then you use the duality, which I showed you, where these basic moves are just dual to a bifundamental, a flavor U1 and two other bifundamental, and you glue them back together, and what you obtain is exactly the mirror of your initial N=4 quiver gauge theory. So this is very nice. What we wanted and we are trying to do is to generalize this also to N=2 gauge theories, and again we use the same reasoning. This is based on a working project that we are doing at the moment. We again start from the N=4 basic moves, and we apply the same real mass deformation, planarizing the theory on one side, while making the theory chiral on the mirror side. And again, what we obtain in this case is that the single bifundamental gets reduced to a single chiral bifundamental on one side, while on the left, what you have is that you have the limit of these T of SUN theories, which are these two big triangles where each UN gauge node got X to the maximal torus, and these are glued together with a single chiral. And the statement is that all of this theory is actually S-confining to a single chiral bifundamental. Also note that for this S-confinement to be true, you also have very specific fixed values of the background Chern-Simons level on the right for the SUN X global symmetry and for the SUN Y global symmetry. On the left, you have specific Chern-Simons level at level 1 for all the gauge nodes, and you also have mixed Chern-Simons interactions and Faliette-Iliopoulos terms, which actually, once the theory enhances, gives you the global symmetry, which is mount to SUN on the right side. So all of these are necessary to have the correct identification of theories. And once that we do this with this basic move, and also with the fusion to identity and with the inverse basic move, we are able to generalize this discussion to a vast class of theories. So here I'm showing you the example of UN with F1 plus N fundamentals and F2 plus N anti-fundamental. These are UN gauge group. Again, note that the Chern-Simons level are very specific for this reason to go through. Again, this comes from the fact that this is a theory which comes from a deformation of an n = 4 duality in the beginning. So again, you do the reasoning as before. I will not do it, but you chop up this theory in simple blocks, which you are able to dualize using the basic moves, which I showed you. And what you obtain in the end is that this is the mirror symmetry. This beast is the mirror dual that you obtain once you perform these steps. And okay, so which class of theories are we actually able to reach through this algorithmic strategy? So we are systematically able to study the UN theories with this Chern-Simons level. So for the SUN, you have F1 plus F2 divided by 2 Chern-Simons level, while for the UN, you have F1 plus F2 divided by 2 plus N Chern-Simons level, with either F1 plus N fundamentals and F2 plus N anti-fundamentals, or F1 plus 2N fundamentals and F2 anti-fundamentals, or vice versa, with F1 and F2 greater or equal than 0. I want to point out that these are not the only theories to which this strategy of just taking the n = 4 pair and applying the deformation works, but these are the theories that we can currently reach through this algorithmic strategy. And moreover, you can also do a further generalization, because observe that in all of these cases, you just have this plus n. So in this more general form of Chern-Simons level, I just discovered a theory where L is equal to 1, but you also can apply the strategy to more general theories where this Chern-Simons level for the U1 is different from this one. So what you do is just that you do a procedure where you're gauging the U1 topological symmetry of the UN, in this way going to SUN at the level F1 plus F2 divided by 2. Then you introduce a background Chern-Simons level, which is delta L equal to L minus 1 for the baryonic symmetry. And then you gauge back the baryonic symmetry to go back to the UN with exactly these Chern-Simons levels. So we are also able to change the U1 Chern-Simons level through this procedure. Now I wanted to show you a couple of examples which show what kind of non-trivial prediction these new mirrors let us do. So this is the mirror of U3 with 3 fundamentals and 3 anti-fundamentals at level 0 for the SUN and 3 for the U1. This is the mirror that we claim. The black nodes are again at level -1. The blue node is at level -3 alpha, and the red node is at level -1 alpha. And what you see from the mirror is that, first of all, there are no mesonic gauge invariant operators which you can build, which tell us that there are no, on the left side, monopole or dressed monopole 1/2 BPS operators, which this could map to, parameterizing the moduli space. And also, since you have an SUF manifest flavor symmetry on the right side, this has to map on the left to the topological symmetry. So this tells us that the U1 topological symmetry on the left actually has to enhance to an SU2 topological symmetry in the IR, which to me doesn't seem at all trivial. So another quick example, in this case, we just flip one of the fundamental, which became an anti-fundamental. And we see that what changes on the right side is that the SU2 flavor symmetry has been broken to a single U1 flavor symmetry. This U1 flavor symmetry is rotating the single meson gauge invariant operator that we can build, which is just built by starting from a square U1 and ending to the other. So again, in this case, we don't have an enhancement of topological symmetry on the left, but also it tells us that this mesonic operator has to map to some monopole or dressed monopole operator on the left side. So this duality tells us that also on the left side, there must be some dressed monopole operator parameterizing the modular space, which is mapped to this meson, which again is not a trivial statement. Also, I wanted to point out that this is a theory which is not, which we cannot reach by applying systematically the algorithmic strategy which I showed you. But again, you can see that we know what the mirror for this theory is. You can still apply the same reasoning where you start from the n=4 mirror pair, which is in this case will be the n=4 U3 theory with 6 flavors and its mirror. You apply the deformation, and this is exactly what you get. In this case, you apply the deformation in such a way that you're giving a positive mass to 4 fundamentals and to 2 anti-fundamentals. So in the left, you obtain this electric theory. And if you map this deformation carefully on the mirror side, what you obtain is exactly this mirror. So again, what are the applications of this strategy? So with the described procedure, we're able to describe a vast new family of n=2 SQCD-free dualities. So I showed you the example of SUN at level K with F1 and F2 chirals, where the Chern-Simons K is actually the lower bound, the lower value of this bound. But actually, what you can do is obtain just further generalization of this by just starting with these theories and then giving some positive real mass to some fundamentals or some anti-fundamentals. In this way, you're able to reach also theories with higher Chern-Simons level. So in the end, we are able to prove exactly this vast class of theories with our kind of deformation. So SUN at level K, where K takes this value, and also UN at level K, comma K plus Ln, where L, as I showed you, can be a generic integer, while K is again has to satisfy this bound, as well as generalization to linear quiver theories. I showed you the example of T of SUN, but you can also apply it to more general quiver gauge theories, also with uneven rank. What are the interesting features of these dualities? As I showed you, is that the interesting feature is that the mirror is completely Lagrangian and abelian and also planar. As I showed, they enjoy a rich phenomenology for specific values of n, f, k, and l, such as chiral symmetry breaking, S-confinement, SUSY breaking. They present TQFTs and much more. So they have interesting features to study. And also the study of the massive phases of these theories could lead us into having some new insights of non-supersymmetric dualities. And as I showed, following the work of n=4, of the algorithmic approach in n=4, we are able to generalize and extend this algorithmic approach also to mirror symmetry for this vast class of n=2 theories. So what are the outlook and the future perspective is that I presented to you a strategy which lets us derive a vast new class of n=2 mirror duals for SQCD in 3 dimension with gauge group both SU and U, chiral matter and non-zero Chern-Simons level. I showed you some examples of the procedure. And then I gave you some tests of the proposed dualities in terms of the matching of the rank of global symmetries, the matching of S3 partition function, and the matching of superconformal indices. Then what we can try to do now and what we'll try to do in the future is take these n=2 dualities and try to maybe break further SUSY to n=1 or even to n=0 and to maybe reach some non-supersymmetric dualities. Also, some questions that we are asking ourselves is that, okay, there are some brain interpretation for n=2 theories. So what could be a possible brain interpretation, sorry, brain setup interpretation for these n=2 dualities that we came up with? And also this strategy could be applied in the future to quiver gauge theories with different gauge nodes, also to quiver gauge theories with USP gauge nodes, SO gauge nodes, and so on. And okay, thank you. I finished my presentation. If there are any questions, feel free to ask. Thank you.
Right. Let's thank Gabriel. Do we have questions? So do you, if you start with something like where one side of the 3D mirror symmetry is not Lagrangian, could you like do something here? Like, have you thought about this? Like
Actually, yes.
the E-type unitary quivers, which are like then dual to some 3D minimal Schansky or something like this.
Yeah. Actually, this strategy could still be applied. There are, I don't know about applying it to these Minan-Nemechansky theories, but we tried applying it to these improved by fundamentals like the FM and the FE theories, which are strongly coupled theories. Sorry, okay, they have a UV Lagrangian description, but when you consider them inside of bigger theories, when you're actually gauging the emergent symmetry, they become no Lagrangian anymore, even the UV. So you can try applying this strategy in the UV, but I mean, for the moment we didn't get anything too interesting, but we still try. I mean, you can definitely apply the strategy. The strategy still works. You're still able to obtain some n equal to mirror pairs. And also, so okay, these theories that I told you are already themselves n equal to, so you can also start from some n equal to mirror pair, which is already known, and then apply again this planarization to these mirror pairs and see what you obtain. It's possible.
So directly to an English 2 pair.
Yes, indeed. Like for to the FM theory is an n equal to theory. You can try to apply this deformation. Yeah, exactly.
Cool. Some really crazy planar diagrams you have.
Yeah, yes, indeed.
So one very quick question. The potential, the superpotential, the planar part is always like right loops are positive, left loops are negative.
Yes, that's actually the choice that we had for the superpotential, because of course you can do a field redefinition to change the sign of this superpotential, but we wanted to make it consistent also with 4D dimer models. There could be a connection to 4D dimer models, but you see
That's why
that.
I'm asking, like,
Yes, in addition to this cubic superpotential, you also have these monopoles, these extra monopoles in the game. So, I mean, you have to be careful. There could be also some connection to dimer models. We didn't really investigate these, where maybe these are some quivers which come from some possible dimers on the plane, but we don't really investigate this too much.
Good.
Thank you.
Thank you. Do we have more questions?
Yeah, I had a quick question actually. So you only did Higgsing on one side of the duality, that's starting from the 3D n equals to 4 mirror.
Exactly.
Now, in principle, you could think of doing like Higgsing on both sides, right? So for example, you could break SUN to, I don't know, UN minus 2 times U1 or something.
Yes.
So do you get new dualities that way, or is it like, your...
Okay, so in the example that I showed you, we always try to keep the SQCD theory chiral, but what you can do is actually try to keep the mirror theory chiral. So on the chiral side, on the mirror side, you will just obtain a longer chiral quiver, and then your SQCD will actually get a joint Higgs. But the point is that when you fixed a choice of which theory gets a joint Higgs, it seems that the mirror theory automatically has to become chiral, so not Higgsed. We didn't find some solution where both theories actually were Higgsed. Or maybe there are some intermediate choice where both sides get only partially Higgsed. Because in these examples that we studied, on one side is always complete, like fully adjoint Higgsed, so from UN to U1 to the N, and the other side is completely unhiggsed. But there could be some intermediate situations where one of the two sides is maybe partially Higgs and also the other, but we didn't find any, so maybe it's not possible. But definitely what we tried doing is like taking a planar limit on both sides and seem to be impossible. Like these are two vacua which exist, like a vacuum where both theories are planar exist, but they just don't map into each other. So it seems that the chiral vacuum on one side, for example, on the electric side, has to be mapped on the planar vacuum on the mirror side. We cannot map the chiral to chiral or the planar to planar. This is at least from our results, what we got.
I see. So if you're saying that if you demand planarity and chirality on one side,
yes,
then none of these other theories or other dualities that you get fit the bill. Is that correct?
exactly.
Okay.
Yes.
Okay, thanks.
Thank you.
Do you need to consider the boundary condition when you think about this mirror duality?
The boundary conditions, you mean from the point of view of string theory, boundary conditions?
No, the boundary condition for the chiral multiplet on both sides. You have D boundary condition and boundary condition.
So you mean like to the class of theories that we applied, like the condition on the Chern-Simons level? Which boundary condition?
Yeah, for CD theory, you usually need to have a boundary condition, right? If CD theory have a boundary, so for each chiral multiplier, you can have a D boundary condition and N boundary condition. So I get it's also
okay.
that's my understanding. So,
okay, but that's if you want to do the, like, as far as I know, if you want to do the string theory interpretation when you have your D3 brains, which and on NS5 or D5, you need to put some boundary condition on the D3, and these boundary conditions are actually fixed on the choice of the fact that you are ending them on NS5 or D5. So in our case, I don't really know. Like as I said, we didn't really look into brain setups. So if we were able to look into brain setups and maybe see what actually happened with the freezer, we actually expect that since you have theories with Chern-Simons levels, the brain setup will involve PQ web and the free brains ending on PQ web. So with some particular choice of boundary condition of this D3, whose low energy theory will give you 3D n equal to gauge theories with Chern-Simons levels and chiral matter. So yeah, this makes me think that okay, maybe this deformation you can also perform it at the level in string theory at the level of the brains. What you can do is just rotate some of the D5, then them on top of the NS, forming PQ webs, and then you take some part of the PQ web to infinity. This amounts to giving positive real mass to some either fundamentals or anti-fundamentals. And you will take some n equal to brain setup, but we didn't think too much about this.
I think I do not mean the boundary condition for the deep brain. So I mean directly as boundary condition and Neumann boundary condition for the for the matter field. So
for the matter field.
Yeah, this is useful. So because if you consider some half index, which is similar to vortex partition function, but you with half index also contain the contribution from the boundary. So
I see.
So usually so the middle symmetry would change the boundary condition from D to N or N to D, because here you have so many matter. So so the matter on both chiral multipliers on the electric theory side maybe looks simple, but the matter on the magnetic theory side looks very different. So I'm asking if the boundary condition is interesting.
We didn't look at boundary conditions, so I don't know. They could be interesting, but we didn't try looking at them. I'm sorry.
I don't no problem. Thanks. So I have another question. So
yes,
I remember that in some paper, maybe in some older paper. So So people use some brain to realize to engineer those monopole potentials. So I'm wondering if this monopole potential, in their construction, their monopole potential is that similar to the monopole in the field potential that you discussed.
I'm not really familiar with these ways of engineering the monopole superpotential. So in our case, it's actually necessary because of the adjoint Higgsing. So it's the adjoint Higgsing of the gauge groups what makes these monopole superpotential appear for consistency. So I don't know, with some procedure to... So you mean engineering them from the point of view of the QFT, so not the brain setup?
From the brain setup. So maybe some people
from brain
in
setup.
19
Okay.
yeah, maybe some people in 1997.
Yeah, probably.
At that moment there's some brain constructing for the 3D theory.
No, I agree that
so
okay, definitely there are so yeah, I agree that probably the n equal to definitely the n equal to brain setup for both these theories could be built. Okay, maybe realizing this cubic superpotential is more difficult. But yeah, maybe if we're able to have this brain setup and understand this duality at the level of the brain setup, maybe again as a mesh duality would be interesting and could lead us to more insights. This class of duality, maybe also finding some more general dualities again, inspired by the brain setups, but we still have to probe that direction. We didn't look much into it.
I see. But did you think about using some 3D correspondence to engineer this 3D equal to mirror duality? I think if you ignore this monopole potential, so this abelian theory with some mixed consensus level can be engineered by some three manifolds. So such as the DGG construction of some plumbing manifolds with this abelian thing. Also mixed consensus level can also be realized, I guess. But the monopole potential, so I don't know how to do that. How to use the CDC correspondence to
engineer the monopole superpotential.
Yeah. I don't know. Did you think about this?
No. We didn't actually. We didn't, and it would be something interesting to explore actually, to understand how this monopole superpotential can be engineered. Maybe it could lead us even into getting better insights on how these are generated. So,
I see.
Yeah.
Thanks very much.
Thank you for the question. Thank you very much for the question.
Do we have more questions for Gabriel? All right, well then let's thank him again. And we can go off the record.